Okay, so we're recording the meeting. Let's begin the lecture today. We got the 29th of July, Wednesday, and we're in the midst of a fascinating discussion. We're looking at the behavior of an arbitrary system. In other words, we're setting up a very general framework. This equation that we've written here, which has a structure of a matrix times an acceleration vector equaling minus a K matrix times the displacement vector. This is a framework that will serve us well. We can examine many different problems where we're looking at the behavior of a system near an equilibrium. Okay, let's take a moment to revisit the topic at the end of our last lecture. Okay, so towards the end of our last lecture, we introduced the notion of normal coordinates, okay? And it's useful to remind ourselves, if you have an n degree of freedom problem here, this lowercase n is the number of degrees of freedom. We're very familiar with the idea of using generalized coordinates q1 through qn to describe this problem. We're very familiar with this from Lagrangian mechanics. Okay, so this idea of introducing normal coordinates, it's really a special case, a special choice of generalized coordinates. Let's take a moment to talk about this in a little more detail. What's happening here in chapter 11, again, this is the overarching structure. I'm pointing at this with the pen. This differential equation, and in general, this is a system of coupled differential equations, all right? The x vector is a collection of displacements. It could be a large collection, right? This number of degrees of freedom could be large. Okay, so this x vector, it need not be a three-dimensional vector or two-dimensional. It could be a very large dimensional space we're talking about. All right, so this is our system of differential equations. And from a point of view of Python, there are many, they call them solvers. In the world of computer science, one speaks of solvers. And there are solvers that are very much, a huge amount of work. Generations of computer scientists have worked on these solvers to really make them fast and accurate. So I just wanted to mention that from the perspective of computer science, this problem is something that's been studied in great detail, and there are wonderful open source solutions. We're interested in theoretical investigations. We'd like to write solutions and formulas. And the useful thing here, one thing we'll see in today's lecture, is that using our theoretical tools to analyze these equations, we can discover certain aspects of the motion that might not be clear if you put it on a computer, all right? Because ultimately, if you run this on a computer, you can only run, for a given run of the program, you're running one case of initial conditions. So our analysis in terms of theoretical tools will give us some great insights. Okay, so again, this is the basic framework for chapter 11. Let's talk about what the author calls the generalized eigenvalue equation. Okay, so this is our, let's write it like so, generalized. So this is a generalization of the usual eigenvalue problem, right? For the usual eigenvalue problem, you have the identity matrix here, and the fact that there's an omega squared here rather than the typical eigenvalue lambda is not really a fundamental difference in structure. It happens that we have omega squared here because we have the second order time differentiation, and this omega originated from a certain ansatz where it was the usual frequency in radians per second. But again, the reason this is called a generalized eigenvalue equation is because we have these two matrices. All right, so let's take a moment to talk about these two matrices and how they relate to the idea here, this notion of normal coordinates. Okay, looking ahead to the final exam, let's be clear. Normal coordinates is not going to be on the final exam. As the final exam approaches, I will prepare a list of topics, and normal coordinates will not be on there. Again, the reason is we have to budget our time. Nothing wrong with normal coordinates, but the point is it's kind of an optional luxury here. We have essentially two ways to solve this problem, okay? This problem here, our goal is to solve the problem as always. Method number one here, we can use this generalized eigenvalue equation. This is the method that is favored in the chapter. Method number two, we've got this wonderful appendix, okay? So again, that appendix is optional reading. The topic of the simultaneous diagonalization of two matrices, okay? What a crazy idea this is, right? And I say that from the perspective of quantum mechanics, where we're told, right? It's drilled into our heads. You cannot simultaneously diagonalize two matrices. Again, the resolution is in quantum mechanics, that statement's correct. And we're talking about transforming matrices when they represent operators, okay? If you have two operators that don't commute, you're not going to be able to find a basis where they're both diagonal, because then they would commute. Okay, Appendix A2, we're talking about transforming these quadratic forms, the kinetic energy, the potential energy, they're quadratic forms, and here we're thinking of the potential energy near an equilibrium. Okay, so we're going to go into detail on what that means. The point again, we'd like to make some closing remarks here on this topic of normal coordinates. You can solve this equation. That's our task. We want to solve for the motion. You can solve this by using this framework, the generalized eigenvalue equation. This is the method that is favored in chapter 11. Alternatively, you can use this interesting material in Appendix A2. And when you simultaneously diagonalize, okay, then you've essentially defined these normal coordinates. So simultaneous diagonalization all right, so let's appreciate what's going on here. Again, it is a wonderful idea, and I should move the paper like this. We've got a pretty good configuration of paper now. Look at that. The idea is if you can simultaneously diagonalize these matrices, so imagine this problem here where the M matrix is diagonal and the K matrix is diagonal. This is truly wonderful because the problem has decoupled. You may have, for example, x7 double dot. Okay, that would be the second time derivative of the seventh of these x variables. And it's just a constant, you know, a negative constant times x7. So this is going to be a familiar chapter 5 kind of topic. You have a simple harmonic oscillator. We know exactly how to characterize the general solution. Okay, so again, this idea of simultaneously diagonalizing the matrices is equivalent to choosing some new coordinates, some very clever coordinates. When you transform to the new coordinates, both of these two matrices are diagonal, and then you can solve the problem with ease, right? No problem there, you can solve it. But again, we're going to view this as kind of an optional approach. The reason is it's somewhat tedious to follow through this program of simultaneously diagonalizing the matrices. It's good to know it exists, and the appendix is a pretty good place to place that material. So let's keep that material in the appendix. We're going to proceed with this generalized eigenvalue equation. Okay. So let's continue the investigation here. We had a wonderful problem with these two railroad cars with massless wheels. So we'll treat the two railroad cars as point masses. We had several springs, and we're interested in the solution. What can this system do for us? Okay, we're viewing this as an example of a case where you're analyzing a system near equilibrium, And there are several modes. These are eigenmodes where everything, if the system is in a pure state, a single eigenmode, then everything, in this case, both of the railroad cars, are moving with the same frequency. They could have phase shifts, but it's the same frequency. So we're going to investigate a special state of affairs, the state of weakly coupled oscillators. Okay. And one of the wonderful stories from classical mathematics a couple hundred years ago, there was a famous mathematician. He was homesick in bed, and there were these two cuckoo clocks on the walls. And he noticed that although, say you have one cuckoo clock over here and maybe another cuckoo clock quite some distance, the two pendula became synchronized. Okay. And the reason is there was some sort of mechanical coupling in the wall. And typically walls of buildings are pretty rigid. There's barely any sort of detectable motion. But the two cuckoo clocks, since they're precision instruments, the fact that there was some sort of mechanical connection between these clocks resulted in the two clocks becoming synchronized. They were not synchronized because they were extraordinarily accurate timepieces. There's almost no way you could take a classical cuckoo clock from a couple hundred years ago and get them to be stable on that kind of time scale. Obviously, they did amazing things with mechanical clocks, and navigating around the globe was one reason to develop highly accurate clocks. But let's talk about how we can use our skills here to examine this fascinating topic, weakly coupled oscillators. Yeah, weakly coupled oscillators. We'll be using this framework again. We know for these two little railroad cars, we've worked out the capital M matrix and the capital K matrix. We do like to consider the case where the two cars have equal masses, right? It just serves to remove a layer of algebra that's just a little unpleasant. So here we go with the famous mu-mu matrix. There you have it. The mass matrix now, under the assumption that the two masses are equal, we have M, 0, 0, M. Okay, now the K matrix looks like this. Okay. We're going to assume that spring constant 1 and spring constant 3, those were the springs that attached railroad cars to these rigid concrete walls. Let's take those to be equal, and we'll simply call those K. Now the off-diagonal element, this is the coupling, and we're going to assume it's small. Okay, you can see I've included a huge amount of space here. I want to be clear, this is a 2 by 2 matrix. The upper left element is K plus K2. The lower right element is K plus K2. And we do have these off-diagonal elements, and we know the off-diagonal elements are responsible for the coupling. And just so there's no hard feelings, I included lots of space to make it clear that we have a 2 by 2 matrix. Okay, so once again, we'll follow the prescription. We have a very clear prescription for how to compute the eigenmodes. We must compute okay, we're going to follow this prescription, the generalized eigenvalue equation. And we know that we must face the music here and figure out the determinant of K minus omega squared M, set that determinant equal to 0. In doing so, we'll have an equation for the frequencies. All right, so we're going to skip the algebra again. We'll grind out the determinant. We cannot waste precious time here going through mountains of algebra. Let's go straight to the solution. there's one frequency, which is the square root of k over m. Again, this would be like the windshield wipers on a car, also called the sloshing mode. The two, oh my goodness, I forgot to move that thing out of the way. All right, so it's okay, we got the document camera going. That's what's really important. As I was saying, this mode here, notice the absence of K2 in the frequency. This is the mode where the two particles move left and right, fully synchronized. So we spoke of the sloshing mode, right, last time. And spring number 2 is never extended or compressed. It never exerts a force. The value of the spring constant does not enter into the physics when you're in this mode, which we're calling mode number 1. Omega 2. Here we do have the off-diagonal element. Okay, so again, the fact that we have weakly coupled oscillators, how would we express that mathematically? The fact that they're weakly coupled is that you have a very weak spring here. This K2 is a small spring constant compared to K. Okay, so weakly coupling, the fact that we have weak coupling can be written like this. Both of the K's are positive, so there's no need to put absolute value signs here. Right, we're thinking of springs with positive spring constants, and we're just saying that this spring constant K2 is much smaller than the K1 and K3, which we're using the symbol little k for both of those springs that are attached to the walls. Okay, so as you know, we have these two frequencies that are nearby. Okay. You can do a Taylor series expansion here and see that this omega 2 is slightly greater than omega 1, right? Because we have a positive contribution here. So it's useful to define some symbols. Okay, and I'm following the text here. Let's define two symbols. A little bit of a cautionary remark. Often when we have an epsilon in our calculations, and if it's supposed to be small, we typically arrange for the epsilon to be a pure number, like 0.001, okay, pure number. Here, this epsilon has the same dimensions as omega naught, so inverse seconds. These are both physical quantities that are measured in inverse seconds, and we'll simply define omega naught to be the average of these two frequencies. Okay. So far, so good. And we'll define epsilon to be the excursion away from this average. So omega 2 is slightly greater than omega naught by epsilon. And so, of course, we can write that out. It'd be omega 2 minus this omega naught, etc. But it's simpler just to say omega 1 okay. So this fully defines as epsilon. It's the offset relative to the average. Okay, so going forward, we're going to prefer not to talk about omega 1 and omega 2. We'll be talking about omega naught and epsilon. This will be a useful way to organize the various calculations that we're going to launch into. And one of the key words here is systems with different time scales. And I mentioned earlier in the course, there are entire conferences devoted to studying systems with different timescales. Okay, fascinating stuff. Our own lunar orbit, right? Our moon orbiting our planet. We have some interesting stuff going on. Once a month, the moon goes around the Earth, and then on a much different timescale, the Earth-Moon system orbits the sun. Okay, so we have some interesting stuff going on. We'll say the fast motion is the motion of the moon around the Earth. We'll call that the fast motion. And then the Earth-Moon system is slowly going around the sun. What are the results? Well, the orbital plane of the moon around the Earth, they really orbit the common barycenter, it precesses, right? It's not fixed in space, as you would say based on chapter 8. If you had a problem with just 2 point particles, you know that the orbit is confined to a fixed plane. But because we have 3 particles now, the distant sun and the Earth-Moon system, there's a precession, okay? And you can work out the precession. Every 18 years, the normal vector to the moon's orbit precesses. And then it gets even more complicated. Every 9 years, the semi-major axis of the lunar orbit, which of course is in that plane we just discussed, every 9 years, it goes through one cycle. So it's slowly moving in that plane. So these are some of the fascinating things that can happen when you study systems with different timescales. Our friends in chemistry, right? So as I was working on my PhD in the 90s, we would sometimes meet with chemists, right? Which is, the building is pretty much right next to the physics buildings. And some of these people are interested in molecular, you study a molecule, there are vibrational motions. And these vibrational motions occur on a very fast, high frequency. So the period's very short. That's a fast motion. And then the molecule can slowly rotate. So that would be, again, an example of a system with 2 different time scales. So what we have here, so for this problem with the weakly couple, with the weak coupling, right? We have weakly coupled oscillators. K2 is small. This epsilon is much smaller than omega naught. Let's observe. We should really state that clearly here. And again, there's no need for an absolute value sign here. This epsilon per definition is positive, right? Because epsilon is the excursion, the difference between omega 2 and the average. And we know that omega 2 is the greater of the 2 frequencies. Okay, so this epsilon is a small frequency. Again, measured in inverse seconds or radians per second. So we have 2 time scales. We've got the 2 pi over omega naught. Okay. So this construction here, when we say 2 pi over omega naught, we're thinking of omega naught as radians per second. And so it's natural to construct 2 pi over omega naught. This is the period. There's a period associated with the frequency omega naught. So that's a time scale, right? A period is a time scale. Now this epsilon is very small, okay? So 2 pi over epsilon, this is a much larger, this is the larger time scale. And what we're gonna see is if you imagine preparing the system with the 2 railroad cars, there will be times where one of the 2 railroad cars is oscillating with a very pronounced amplitude, and the other one is nearly motionless, okay? And then gradually energy will be transferred from one of the oscillators to the other. And so if you check back sometime later, which is a quarter cycle of this period, all the energy will have migrated to the other oscillator. So we're going to investigate, this is the kind of physics we're interested in here. There will be pronounced oscillations of one of the railroad cars, the other one nearly motionless, and then gradually energy is transported from the one oscillator over to the other one, and it goes back and forth. Okay, so this is going to be fascinating. We know how to solve this. The structure of the solution, again, is similar to what we did last time with when we computed the modes of the system. Okay, so it turns out the eigenvectors are the same as before. Remember last time we talked about the eigenvectors. There was the 1, 1. There was the 1, minus 1. No change here to these eigenvectors. These eigenvectors are identical to what we talked about last time. The frequencies have a different appearance now, right? Last time we talked about a different problem where we had all 3 springs equal to K. Okay, so we had different frequencies last time. The structure again here with the breathing mode, and you can see physically, right? We want to bring in our notion of the physical intuition here. You still have that breathing mode where the 2 railroad cars move towards each other, then move away from each other. We call that the breathing mode. And you can see that that'll be a solution to the equation of motion because the center of the middle spring is motionless. If the center of the middle spring is motionless, you may as well nail it down. Alternatively, get some machine screws and really ensure that it doesn't move. Then you've fully decoupled the two oscillators, okay? And that's a way to visualize that particular solution. Okay, so here we go. Let's write down our solution. Given that we have this alternative way to write the two frequencies, we have a very enjoyable way to write z as a function of t. If you hear any snoring, it's that cat over there. It's not me. I'm wide awake. But that cat, which sleeps all day, okay, here's the first eigenvector. And we can factor the exponential. We'll write this like an e to the minus I epsilon t. Okay, so again, our general solution here, we're using the complex notation. We have a linear combination of the two modes. And writing it here with the curly braces, we're simply factoring out a shared factor. Okay, so let's take a second to appreciate what we've done here. Let's do this. You see this, there's a shared factor of e to the I omega naught t. If you multiply that into the curly braces, oh, no, this is not okay. This is an epsilon. I'm going to do, well, as it happens, I have some correction tape. Let's just see one of these cool gadgets. Okay, so far so good. All right. So, as I was saying, if you do multiply this e to the I omega naught t back in here, you see you very rapidly get omega naught plus epsilon. We know that's omega 2, okay? And this thing is a -1, right? Okay, and the other one, omega naught minus epsilon, that's omega 1. So this, in fact, is precisely the familiar form that we talked about in our last meeting. For today's discussion, we found it useful to factor out this shared factor. There's a common factor we factored out. Okay, now again, this e to the I omega t, e to the minus I omega t, these are slowly varying. Remember, epsilon is a very small frequency. So what's happening here, you can see already at this stage that there are times, well, actually, it's going to get a little more complicated, but we can see that these prefactors slowly vary. It's too early to say that we can see that the energy goes from one cart to the other. That's going to require some further analysis. But at this point, we have a very clear distinction here with a fast time scale and the slow time scale. Okay, so let's consider a special case where C1 is equal to C2. This will enable us to draw some pictures. Okay, let's say they're both equal. And it turns out it's useful to define, this is our definition of capital A. We define this to be capital A over 2. In other words, capital A is defined to be 2 times C1. Okay, and it's assumed that C1 equals C2. Okay, having said that, we can write our equation as follows. Okay, now I want to emphasize what I'm going to write next is a column vector. Okay, it is a column vector. Again, some of these vectors look funny because they're two-component column vectors. Okay. Yeah, I got tripped up earlier because if you take an epsilon, you rotate it 90 degrees, you get an omega. And we're going to be very interested in 90-degree rotations here in just a moment, and epsilons and omegas. Okay. So that's the column vector. And again, we have this shared factor. Okay. So now it becomes increasingly clear what happens with the energy sloshing back and forth. Because now we know that this upper component, remember, this truly belongs to one of the two particles. The idea of a mode is a shared concept that belongs to the whole system. But this upper component belongs to particle number 1. So its motion, its complex motion is a times the cosine of epsilon t times e to the I omega naught t. Okay. So you can see that the amplitude of the motion is proportional to the absolute value of the cosine of epsilon t. Okay. So let's draw a picture. There's a pretty cool picture we can draw to go along with this. And frankly, I think we can say, let's save ourselves some time. In general, we want to avoid PowerPoint overload, but from time to time, it's useful to just take the old lecture notes here and fold them carefully. Okay, so here's what's happening. So we just observed, we have this solution for the z of t. The real part looks like this. Now this is somewhere, once again, I really want to emphasize, this is a column vector. It sure looks like a 2x2 matrix, right? That's why I emphasize we have multiplication here. I put some dots. I did everything I can do to try and clarify the situation, that this is a column vector. The upper component is cosine epsilon t times cosine omega naught t. The lower component is a product of the two signs. So even though it looks like a 2x2 matrix, there's no space here between these two things. There's a multiplication operator. And so that product evaluates to a single number, and that's the upper component. And this product evaluates to a single number, and that's the lower component. Okay, so at time t equals 0, what happens is you got a 0 downstairs and a 1 upstairs. Okay, that's a special case. And the initial velocity, you differentiate this, we have them both motionless. Okay, so this is a case where you, as the experimenter, you prepared a system where railroad car number 1 was displaced away from its equilibrium in the positive direction. And then you release them both from rest. So both of them are motionless at time t equals 0, and we just have one of them displaced to the right. The amount of the displacement is this arbitrary amplitude. This is fully linear. You can double the amplitude, you still have an exact solution. Okay, so what happens then is we have this interesting structure. So first observe, down here at the bottom, we're going to plot the two solutions. So this is the position of railroad car number 1 as a function of time, okay? And this is railroad car number 2 as a function of time, okay? Again, the fast motion is this omega naught. This is the frequency. If you remove that middle spring, there would be a certain natural frequency to those simple harmonic oscillators. So that's the fast motion here. And then the coupling causes, wait, no, I'm sorry. The omega naught is actually slightly different. So let's correct that statement. Omega 1, that's the frequency you have if you remove the central spring and you have on the left a mass, one mass and one spring, and it has a natural frequency omega 1. Omega naught is very close to omega 1. They differ by epsilon. Okay, so the remark I made was in the sense of the fast timescales and the slow timescales. We have the fast oscillation. This frequency of the fast oscillation is very, very close to the frequency of the individual oscillators if you remove that central spring. But what we're seeing here, again, there's an envelope here. The envelope is caused by the cosine. So the formula here is the cosine of epsilon t. You can think of that as a slowly varying envelope. And here's the very fast cosine omega naught t. That's the familiar behavior of a spring, right? So we're viewing this multiplicative factor of the cosine epsilon t that is a slowly varying envelope. And you can see an inkling of it here. I think I sketched it in pencil at one point. That's the envelope. Okay. So now it's useful to look at this diagram to appreciate what's happening. This diagram here has a horizontal axis, which is the cosine of epsilon t, and it has a vertical axis, which is the sine of epsilon t. And so we're going to move counterclockwise in this diagram as time goes on, t becoming more positive. We go counterclockwise in this diagram. In the first quadrant, both the sine and the cosine of epsilon t are positive. In the second quadrant, the cosine goes negative, sine is still positive. These observations will be helpful later in the discussion. In the third quadrant, both the sine and the cosine are negative, etc. Here's the fourth quadrant. Okay, so at t equals 0, you see railroad car number 1 has a large amplitude. If you study the system after you let go of both railroad cars, car number 1 is oscillating with a very pronounced amplitude. Car number 2, a little bit of motion, and it gradually increases. Okay. Then there comes a time, which is called pi over 2 epsilon, where we have this role reversal. Car number 2 has a very large amplitude and it's oscillating, and car number 1 is nearly motionless, small if any amplitude. Okay. So let's look at how we can understand that energy has been transferred from one oscillator to another oscillator. And again, this will bring in some of these powerful tools with the fast and slow timescales. Okay. Remember from good old first year physics, power equals force times velocity. That statement comes from the well-known work equals force times distance, right? If a force acts over some distance, and of course there's a dot product in there, work equals force times distance. If you have this take place over some small time interval, you get power equals force times velocity. So that's one of our foundation concepts here. Power equals force times velocity. Okay. Let's look at the energy transferred to, okay, we'll define these two systems. So system 1, this is the mass and the spring on the left. So we have a mass, we have a spring on the left. Okay, system 2. That's the mass and the spring on the right, the spring that it attaches it to the wall. Okay, now let's look at the energy transferred from the system on the left to the system on the right over one cycle of the fast motion. So this is the fascinating concept. We have these two systems, and we're going to talk about energy transferred from this system number 1 over here to system number 2. Okay, energy transfer. Okay, so these are the kind of things that people look at when they study these systems with different timescales. And I still, I'm very fortunate, thinking back on my PhD work, to have worked with some of the researchers in the math department, in particular Jerry Marsden, right, and Ellen Weinstein. These are some of the most famous mathematicians in these particular fields that they're working in. And I remember the last time I saw Jerry Marsden, he passed away several years ago, sadly, but there was a big conference in Southern California, very wonderful conference devoted to systems with different timescales. And he has published a lot of papers, including fascinating analysis of spacecraft trajectories. Again, you could have a fast timescale and a slow timescale when you study the motion of a spacecraft. So there are all these different applications, fascinating stuff. And I just mentioned that there's a whole world of, analysis of systems with different timescales. So here's a typical calculation. We'll look at the energy transfer. So it's going from system number 1 okay, over one, we have to talk about the time scale here, over one cycle. So energy transfer from system 1 to system 2 over one cycle of the fast motion. Okay, so this is an opportunity to talk about tension, right? We've seen this on the recent homework. And I was a little apologetic for using capital T for tension, but in my defense, look at the book. When we studied the Foucault pendulum, we use capital T for the tension. Ordinarily, we reserve that for kinetic energy, but sometimes we do use capital T for tension. Okay, so remember some of the most basic rules of the game. If you have a massless string, and we had that, the problem with the cowboy lariat, right? This was a fun problem. We were treating that certain string, okay, for that actual experiment, you would typically have an electric drill to really give you a very high angular velocity, and then a lightweight piece of string, and then there's that hoop, okay? So if you have a string with some tension in it, then here are the rules of the game. It produces a force, and force is a vector. It produces a force at one end and a force at the other end. The magnitude of the force is equal to the tension, and the direction is given by the direction of the string. Okay, so let's be very clear now as we go through this. K2, that's that spring constant for the spring in the middle. Okay, let's talk about K2 times this difference, x2 minus x1. So this is the tension, and how can we convince ourselves? Okay, how can we convince ourselves that this is right? How can we be sure that it's not x1 minus x2? Well, here's the answer. To resolve the sign ambiguity, first of all, if x1 and x2 are equal, you get a 0 here. That's what we want, because that means both of the railroad cars are displaced to the right by the same amount. So there's no extension or compression of that middle spring. Okay, wonderful. So it works for that case. Now suppose x2 is greater than x1. So this difference is positive. Okay. Well, if x2 is greater than x1, and remember, car number 2 is the one on the right, then what we have is the spring has been lengthened. We're stretching the spring, and therefore there's a positive tension. So that's the kind of sanity check you want to do here. The tension is positive if x2 is to the right, if x2 is greater than x1. So that's precisely what we have here. So now we can proceed with confidence. It is with confidence that we can say minus K2 minus K2 times x2 minus x1. This is the contribution to F2. The contribution from the second spring to F2. And remember, for one-dimensional problems, we don't have to write an arrow over the vectors. This is a vector, but for one-dimensional problems, you can just use the fact that real numbers can be positive, negative, or 0. That's precisely what you need to express a one-dimensional vector. F2 was our notation for the total force on particle number 2. So this is the contribution coming from that middle spring. Having said that, we can now use good old power equals force times velocity. Okay, and it is force times velocity. The velocity could be negative. Perfectly valid. So let's be clear then. We're talking about the power, the rate at which energy is transferred to system number 2. The rate of energy transfer, that's the power. Okay, so power equals this thing here, minus K2 times X2 minus X1 times X2 dot. Right, X2 dot is the velocity. What's the speed? It's the absolute value of X2 dot, but we need the velocity, X2 dot. And all this stuff here, including the minus sign, that's the force. So this is the power. This is the rate of energy transfer to system number 2. Therefore, we can work out the energy transfer. We'll say delta E, okay? That's pretty good notation, right? We're talking about a finite chunk of energy, a finite amount of energy, delta E, transferred from system number 1 to system number 2 over one cycle, right? Over one cycle, how much energy gets transferred? Well, our notation is, we like to write a loop integral for one cycle, power dt. Okay, and so this will be, remember a fast cycle, we know that's 2 pi over omega naught. Okay, here's the integrand, we're going to plug that in. Okay, and let's observe that there are going to be some very nice simplifications. And let's understand how we can argue that these things simplify. We're going to observe that part of the story here is x2 times x2 dot, and we're going to observe that that's a perfect time derivative. It's the time derivative of 1/2 x2 squared. Okay, so let's write this out clearly. The energy transferred from system number 1 to system number 2, we're going to integrate. I'll pull out the minus sign. We got a minus in integral K2 okay, and we're integrating over one cycle. Remember, one cycle is 2 pi. The time duration is 2 pi over omega naught. So that's one cycle. And you can go from 0 to 2 pi over omega naught. You can go from minus pi over omega naught to plus pi over omega naught, doesn't matter, as long as you integrate over one cycle. Okay, so again, the really cool thing is that part of the calculation here involves x2 times x2 dot. We don't need to know anything more about x2 as long as it's periodic. The fact that that's the derivative, that's a perfect time derivative. So we can drop that term. Okay, sorry about that. So now we're left with this integral. We dropped the x2 dot, right? Because it's a perfect time derivative. If you integrate over one cycle, you get a 0. Okay, so now we must answer the question, what's going on with this x1, x2 dot? Okay, so we plug in, we had the solution on the previous page, right? Let's plug that in. This K2 is a constant, we pull out the K2. We're going to integrate over one cycle, and it's an A1 cosine of omega naught t. A2, there's an omega naught here. Hang on, we got an omega naught because there's a derivative. A2 cosine omega naught t dt. Okay. And here I've used the symbol A1 for the amplitude. Remember we showed on these notes here, we have these, the amplitude has a cosine. For A1 we have the cosine, and for A2 we have the minus I sine. So that was for the complex, and then when we went to the real, we had this structure here. The amplitude has a cosine epsilon t and a sine epsilon t. Okay. All right, And so the structure that emerges here, if we assume these amplitudes are fairly constant over, this is the crucial thing, we assume these amplitudes A1 and A2 are fairly constant over one cycle of the fast motion. And that's the crucial thing with the two different time scales. Then we can pull these amplitudes out of the integral, and we use this time-honored result that the time average of the cosine squared is 1/2. Okay, so we're looking at K2, A1, omega naught, A2, and then we remark the 2 pi over omega naught. That's the duration of one period. So if you're averaging, this cosine has an average value of 1/2, you're talking about a 2 pi over omega naught times the 1/2. Right? And again, that's because the average value of the cosine squared is 1/2, and 2 pi over omega naught is the duration of the interval. That's the length of the interval in the time axis. So there's our answer. We can clean up a bit, and we're looking at pi K2 A1 A2. Okay, and so this is very interesting. Now we can return to that picture. Remember, we had this nice picture. Let's see if we can position this properly on the document camera. Sorry, I've got to fold it one more time. Sorry about that. I've got this thing folded and properly positioned. Yep. So, so we see that in the first quadrant here, the product is positive, and we have energy transferred from the first oscillator to the second oscillator. In the second quadrant, the product A1 and A2 is negative, so energy goes the other way. In the third quadrant, again, that's what's shown down here. Let's position it like this. Okay. In the third quadrant, again, the product A1 times A2 is positive. Energy is transferred from oscillator 1 to oscillator 2. So this portion of the diagrams down here where we have a horizontal time axis, the third quadrant is this third of the 4 fundamental pieces of the story. And you see oscillator number 1 is losing energy, oscillator 2 is gaining energy. And finally, in the fourth quadrant, the cosine is positive, the sine is negative. That's the cosine of epsilon t, the sine of epsilon t, and energy gets transferred back. So this is a very interesting discussion to see how we do have different time scales in this problem. And this is a case where we averaged over the fast time scale to see how energy was transferred from one oscillator to the other. And so this was the energy transferred over one cycle of the fast motion. Okay. Of course, the units work out, right? K is a spring constant. Typically, in first year physics, you talk about the energy in a spring, it's a 1/2 kx squared. In terms of a dimensional analysis, K is joules per square meter. So the units work out just fine here. Okay. So next, we're going to talk about the time-honored problem of the double pendulum. We studied the usual pendulum in great detail. Let's talk about the double pendulum. There's no question we've got these two pendula coupled here because they're directly attached to each other. Okay, double pendulum. Okay, so what is the double pendulum? Well, as for the ordinary pendulum, let's draw a picture where we have a rigid ceiling. You actually don't have to have the rigid ceiling. And there are times where you must dispense with the rigid ceiling. But it's useful for a first time drawing the picture to have a firm grip on reality, so to speak. We'll think of the ceiling. There's the ceiling shown as concrete. We have our first pendulum. At this point, you have a standard pendulum that can swing back and forth. As you know, there are times where we get rid of that ceiling and just have a pivot point. So you, as the experimenter, you need to create some apparatus that has a fixed pivot point but allows the pendulum to swing over the top. No problem. It can be done quite easily. Hint, axis perpendicular to the page here. Okay, now we're going to attach another pendulum here. Okay, and looking ahead to chapter 12, first let me straighten out that I do not like how this ended up rather crooked. So looking ahead to chapter 12, the double pendulum is a chaotic system, okay? There's a way to make that a very rigorous statement. What does it mean to exhibit chaos? And when we study chapter 12, as you know, that's going to be the last thing we do in this course, because chapter 12 is not good for the final exam. So chapter 12 will not be on the final exam, but nevertheless, fascinating stuff, just not really appropriate for a final exam. We're going to see that the double pendulum, this is a 2 degree of freedom problem, right? You need 2 angles to specify the configuration. Okay, and so we'll use a phi 1 here. And phi 2. Notice for the second portion of the pendulum, we have used a vertical reference line. So phi 2 is referred relative to the vertical. Perfectly okay choice. You could have done things differently. You could have specified the angular orientation of this second pendulum relative to the first. That is, you could have drawn a straight line extension. You could have drawn a reference line as a straight line extension of the upper pendulum. And you could have measured phi 2 relative to that. Perfectly okay, and very much in the spirit of Lagrangian mechanics, where you're free to choose coordinates as you like, as long as you can clearly state the classical configuration. Remember the classical configuration, if you take a photograph of the system, what's all the information carried at that instant in terms of its overall position, the positional orientation of everything. So for the double pendulum, these 2 angles are a wonderful choice, okay? So then the parameters, in general, we allow these to have different lengths. Notice that's a regular capital L, because we're going to be talking about Lagrangian pretty soon. Those must be the cursive capital L. So we have 2 lengths, M1, M2. We have 2 lengths, we have 2 masses. There's the apparatus. It's understood that this is going to swing in a plane. You can accomplish that by making a 3-dimensional pendulum, and simply by choosing the initial conditions to be in the vertical plane, the system will remain in the plane. Alternatively, you can construct this with hinges, and the hinges allow only for motion along a 1-dimensional angle. Like a hinge here would allow for this phi 1 motion, and a hinge here would allow for phi 2. In any case, the summary is it's a 2 degree of freedom problem. Okay, so we're going to figure out the Lagrangian. Yes, indeed, we must figure out the Lagrangian. And in doing this, capital T once again is kinetic energy. The kinetic energy of mass number 1 here, we're assuming the rods are massless. Okay. You can repeat this problem with massive rods. It's actually, the level of difficulty is actually the same, but just a little more bookkeeping. So for simplicity, let's have these rods be massless. And if the motion is fairly tame, you could use string, right? Because if the system's kind of near vertical, we're not insisting on small oscillations, but as long as you keep the motion within reason, the string won't go slack. And you will again have precisely this system. Notice, for example, if M2 swung way up here, became nearly vertical, then if you had string, the string would go slack and the mass would just fall straight down. So there are times when we must insist that these are rigid rods. Kinetic energy of particle number 1, the familiar 1/2 the mass, m1, the square of the velocity, okay. The potential energy, again, there's some freedom here. You can choose the 0 wherever you like. I'll follow what we have here in Taylor. Okay, so obviously there's an additive constant here, an arbitrary additive constant. Why would we do that? Well, looking ahead to our analysis, we're going to be very interested in the motion near equilibrium. And we're thinking of the equilibrium where both masses are hanging straight down, so the angles are both small. At equilibrium, the angles are both 0. So near equilibrium, this cosine is close to the value it has at equilibrium, which is 1. Okay, so at equilibrium, you've got a 1 minus 1, that's 0. And near equilibrium, the cosine is 1 minus 1/2 the angle squared. So this becomes a small positive quantity. So in summary, the motivation for having this additive constant here is so that the potential is 0 at equilibrium. It's just convenient when we later do a series expansion about equilibrium, there's a certain constant term which vanishes. Okay, so far so good. That's the situation for the first mass particle here. Now, how about the kinetic energy of particle number 2? Okay, it's a fun calculation. Here, you must be cognizant of the velocity vector. Okay, so let's work out the velocity vector. Looking at this picture here, if you have some value for phi1 like this and some value for phi2 like this, and furthermore, if there is a rate of change, a phi1 dot and a phi2 dot, what can we say about the velocity vector of that second particle, m2? Okay, a very streamlined way to write this okay, so what we've done here is we've introduced a couple of unit vectors. There's a phi1 hat. This is a function of phi1. It's a unit vector and it is a function. Let me be very clear. I'm talking about this unit vector. It is a function of phi1. Right? It's a function of that coordinate because it points in the direction that you go when you increase phi1. That's a pretty standard notion for unit vectors. Think of spherical coordinates. You have r hat, theta hat, phi hat. These unit vectors point in the direction that you go if you increase that coordinate and hold the other ones constant. All right. So it is in that spirit we've defined this one. How about this phi2 hat? This depends on both the angles. So the phi2 hat, okay, look at this picture here. If you, okay, wait a second. No. This one does not. This one depends only on phi2. So that's a function of phi2, sorry. If we had defined phi2 relative to the extension of the upper part of the pendulum, then we would have had some complications here. But this is a function of phi2. Okay. So, and notice this is a vector sum. So the velocity vector of this mass here is the sum of these two velocity vectors. Okay. The crucial thing, and we're going to skip some of the algebra here, is that we're going to show that the dot product Okay. Um, here's how this reasoning goes. We have the phi 1 hat. Remember, that's a unit vector that points in the direction you go if you increase. Right, so here's the phi 1 hat. And then we have the phi 2 hat. That's the direction you go if you increase phi 2. Okay. So the question is, what's the dot product of those two vectors? Now in this picture, we drew them rooted at different origins, but in the spirit of a vector space, if you have a vector space, all of the vectors must be rooted at the origin. So you can take this phi 2 hat and simply scoot it over here without rotating it. So we're interested in the dot product. What we do is we note that the dot product is a rotational invariant. So the dot product of these two phi's is equal to the dot product of, you could introduce some radial extensions, right? So you could put an R2 hat here. It's not necessary for the problem, but it's helpful to observe that the dot product of the two phi unit vectors is equal to the dot product of the two R unit vectors. They would be like this. Okay, and that's just the angle between them. So cosine of phi 2 minus phi 1. Okay, so in summary, we can work out, if you square this vector to get the speed squared, obviously there's a term where you dot this into itself. That's very easy because a unit vector dotted into itself is easy to evaluate. It's just 1. Okay, in summary, we got the T2. Okay, there's that first term coming from this dotted into itself. Then there's another term I like to write like this, L2 squared phi dot 2 squared. That's a term from this dotted into itself. And then there's a cross term where you have the dot product like so, 2L1, L2. Okay. All right, so we got the phi 1 dot, the phi 2 dot, and then the dot product of the two vectors. And that's going to be the cosine of phi 2 minus phi 1. Okay, so then there's a similar calculation for U2. We have two contributions, right? There's a contribution as before, basically getting you the z coordinate there, and then there's a z coordinate here. So U2, M2G, and then again, the same construction. We have the L1, 1 minus cosine, like so. And again, this is a familiar construction. The 1 minus cosine here telling you how far you have moved vertically above the equilibrium at the very lowest point. We need this L1 factor. For the other portion of the pendulum with the L2, we have L2 times the 1 minus cosine. All right, we got the Lagrangian. Yep, this is always a major milestone. It's a time to feel good about the calculation. Things are going very well. Once you have the Lagrangian, we have a clear prescription for how to get the equations of motion. Okay. The problem is it's going to get really messy because of this terrible cosine. We have a cosine, there's a phi 2, a phi 1. We've got the coordinates themselves in the kinetic energy. That's going to put a hurting on us. All right, this is not going to be pleasant. So the good news is we're in chapter 11. We're really interested in oscillations about the equilibrium. Okay, so we're going to do a small angle approximation. We've talked about small angle approximations quite a bit. There are times where we go to first order. That's typically when we have the equations of motion. Here we have a Lagrangian. We're going to go to second order. So small angle approx. And it's important to appreciate we're going to second order because we must differentiate the Lagrangian. At that point, we'll want to go to first order. So small angle approximation, sorry about that. Small angle approximation going to second order. Okay. And so if you go to second order, then there are the following general truths. The sine of an angle is approximately equal to the angle itself. The reason is the next term, if you look at the Taylor series for the sine, the next term is the cubic. There's the linear term, the quadratic term vanishes, and the next term is the cubic. But we're going to second order, so we're happy stopping here. The cosine, okay, so there it is. We've gone to second order. Here for the cosine, we do have something interesting going on. Remember, we've done a lot of calculations where we go to first order, but kind of the overarching principle is those were times where we already had the equations of motion, differential equations that you solve to get the motion of the system. Here we have the Lagrangian, and we must go to second order because we're going to differentiate this to get the equations of motion. Okay. So having said that, we can simplify. Let's just observe the kind of things that simplify. There's no need to change anything here, right? The T1 is simply a constant times the phi1 dot squared. No change. It's already exactly correct to second order. In fact, it's a second order polynomial in phi1 dot. All right, so far so good. The interesting stuff occurs here. This is where we have some good news. Remember orders in smallness. We have phi1 dot, we have phi2 dot. This is already second order in smallness. So the cosine, we could put a very accurate series in, but there's no need. We're only going to use the leading term, which is 1. Okay, so that's the really good news here. And so our kinetic energy, we can just summarize verbally. We know what's going on with the T1. We know what's going on with the T2. It's simply that you delete this cosine and just leave it, approximate it as 1, meaning you can simply delete it. Okay. And for these cosines here, we must go to second order. They're going to be very similar to simple harmonic oscillator potentials, second order in the angles. Okay, so we have the Lagrangian. Then from the Lagrangian, you get the Euler-Lagrange equations of motion. Okay. So I'll simply write Euler right. There's the well-known prescription. We must differentiate the Lagrangian with respect to phi1. We must differentiate the Lagrangian with respect to phi2. We must also differentiate with respect to phi1 dot and phi2 dot. Then there's a certain total time derivative, etc. We can summarize the result very neatly. And we welcome this. Obviously, we have a phi vector now. The phi vector is a two-component vector. There's a phi1 upstairs, a phi2 downstairs. This is a double dot, second order time differentiation. Okay, so this is kind of a watershed moment for us. This rather complicated problem with the two-dimensional, the double pendulum. Using the small angle approximation, I can tell you right now, it's no longer a chaotic system. The chaos comes from the nonlinearity. Okay, this system is not chaotic. We can write down an exact solution for this system here. We can write that down, and that's what we're going to do. Let's just take a moment to appreciate the notation here. Obviously, the phi vector. Phi1, phi2, like so. Okay, and the matrices, right? This obviously is what requires some effort. What's interesting here is that the mass matrix has off-diagonal elements. And that comes about because we have this term here. We did not have that in the earlier problem with the two railroad cars moving on a one-dimensional axis. We didn't have a cross term like this, the product of the two velocities. But now we do. And the result is we have a mass matrix with a very rich structure. Here's our mass matrix. Okay, obviously we do have some terms on the diagonal. Okay, so that's the term in the upper left. I'm going to write this as a large matrix to make it clear. It is a 2 by 2 matrix. Okay, that's the term in the lower right. How about the off-diagonal elements? Okay, there you have it. That's our mass matrix. And again, it's very interesting that we have these off-diagonal elements. Now, remarkably, the K matrix that belongs, that we basically got from the potential, this one has no off-diagonal elements. There's 0. Okay, we got a 0 and a 0. In the lower right, we got the M2GL2. Okay. Now notice this does not have the dimensions of a spring constant as we had earlier. And the reason is we have angular variables. Okay. So, usually we made some remarks earlier. Spring constants are joules per square meter. You can also say newtons per meter. This is joules times meter. Okay, so things are different because we have angular variables rather than linear variables. Okay, upper left, we got the total mass. Okay, the GL1. Okay, so this is important to us now. What we have done here is we've taken the double pendulum, which is a very complicated problem, and we're looking at oscillations near equilibrium. So the pendulum is nearly vertical. Both the two component pendulums are nearly vertical. And there's an interesting story with the modes. We're going to see there's one mode where they both swing to the right and then both swing to the left in a synchronized manner. And there's another mode where they have a 180-degree phase shift. Okay, so let's see. It's going to be, this gets rather messy, so we're going to look at a special case. Okay, and the philosophy here is similar to what we did earlier with the problem with the two railroad cars. We're going to assume that the two masses are equal. And if they're equal, we can just use a symbol m. Same remark for the lengths of the pendulum. Okay. And if you do that, it sure helps to clean up some of the calculations that we're going to do. We're going to see there are two very interesting frequencies, and I hope you enjoy nested square roots. Okay, when you solve for the frequencies, omega 1 is the square root of 2 minus the square root of 2. Okay, it's a nested square root times omega naught. Okay, omega naught is the usual square root of g over L. Very standard frequency when you're dealing with pendulum. And the other frequency, it's a nested square root Okay, so in our next meeting, we're going to go into more detail. Now we do have, I got a question in the chat window. We're going to be talking about solutions in just a moment, but we've reached the 2 o'clock hour. I'm going to stop the recording, and then I will stay here for questions, and we're going to discuss what is going on in the chat window here. So stop recording.